Welcome back to my Learning Quantum video series where I discuss and break down quantum concepts as I learn them. In this video, I'm going to be going over basic qubit states and the basic gates and operations that can be formed on qubits in quantum computers. In this video, I discuss state vectors as ways to represent the probabilities of qubits being measured in different classical states. Two frequently used and pretty understandable states are the 0 and 1 states, and they kind of correspond to what you'd think they would. The 0 state indicates a 100% chance that the qubit will be measured in the classical state 0, and the same goes for the 1 state. Other common states are the plus and minus states. The plus state indicates a state vector of 1 over square root 2, 1 over square root 2, and the minus state indicates a state vector of 1 over square root 2 and negative 1 over square root 2. In practice, though, both of these states simply mean that there's a 50-50 chance of a qubit being measured as 1 or 0 in the classical state. Pretty hard to visualize these states or anything that's happening within a qubit for that matter. For this reason, the block sphere diagram exists to visually represent the state of qubits. There is an x, y, and a z axis, as you can see in this simulator we have here, and a vector of all three are used to represent the state of the qubit. The top of the sphere represents the classical 0 state, while the bottom represents the classical 1 state. So if a qubit was in the 0 or 1 state, the inside vector would point to either the directly up or down direction. If the vector is not pointing directly up or down, though, it means that the qubit is in a superposition. To represent the plus state, for example, the vector would be perpendicular to the z-axis, equidistant from both the top and the bottom, and we can do that here in the simulator. So right now, it's kind of hard to see, but this vector is pointing straight up, and so this qubit is in the 0 state. However, if we use an H gate, which we'll discuss later, this will move, and it will be in the middle. And now there is a 50% chance of it being measured either at the top or the bottom, or like the 0 or 1 state. The vector inside the block sphere can be transformed in pretty much any possible way with any of these types of gates. As you can see, there's half turns, big turns, 180s, and this is made possible through the use of gates, plus to modify the state of qubits. The gates that I'll be going over right now are the X and H gates, two gates that are extremely common and critical to quantum computing. The X gate, or the NOT gate, is the simplest and most comprehensible gate. In terms of the block sphere, it simply rotates the vector 180 degrees around the x-axis. Practically, this would put a qubit in a state of 0 into the 1 state and vice versa. Pretty straightforward. And I'm going to briefly demonstrate that here. So we have a qubit right here, so represented like this in this IBM quantum composer, so we can make simple quantum circuits, and I can put an X gate down. And when we look at the probabilities, if the qubit is starting in the 0 state, it will switch to being in the 1 state, and it will always be measured in the classical state 1. And now if I use another X gate, it will always be measured in the 0 state. So it kind of flip-flops back and forth, and effectively this is rotating it 180 degrees around the x-axis. Wraps up most of what I wanted to talk about in this video. In the next video, I'll discuss more gates and operations that can be performed on qubits, and potentially some simple algorithms. Thanks for watching. Bye.